And now we're in the last part. So we're just going to talk about power series. I'm going to really do some very basic examples. There's a lot you can really talk about. So I'm now back in the OpenStax text, chapter 6 here. So we're just first finding interval of convergence. Okay, so let's look at number 13 here. Let's see, we got this sum here, n equals 1 to infinity, 2x to the n over n. And anytime you're asked for an interval and radius of convergence, just do the ratio test. That's what it's there for. So we'll do the ratio test. And here we have to keep the absolute values, because x could be positive or negative. So same ratio test setup. Okay. Let's clean this up first. So we have a product to a power. So we have 2 to the n plus 1 times x to the n plus 1 over n plus 1 times n over 2 to the n x to the n. Okay. Now let's see what we can kill. Okay, what can we get rid of? Well, I have powers of 2 that I can get rid of. And note, and I also have an x that I can get rid of here. So x to the n plus 1 divided by x to the n is just x. I can shove that outside the limit because it's independent of x, but it comes out as an absolute x. Okay, the 2, absolute value of 2 is 2, so I can just do that. And now I have this part of the limit left over. And I know that goes to 1, so the limit in question is 2 absolute x. So in order for this to converge, I need to find x so that that limit is less than 1, so that 2 absolute x is less than 1, strictly less than 1. Remember, the conclusion of the ratio test says that in order for my sum to converge, the limit in the ratio test has to be less than 1. And so we remember our how to handle our absolute value inequalities. If I have absolute value of x less than c, that means I have minus c less than x less than c. So we just solve here. 2 absolute x less than 1 gives us minus 1 less than 2 absolute x less than 1. Divide 3 by 2. Whoops. That should just be an x there. So I have x is in the interval from minus 1/2 to positive 1/2. So at the very least, I know that my sum converges inside this interval. Wait, what did I just do? Oh, no, that's right. Okay. So I know that my sum converges inside that open set. We have a theorem that says that. But now I need to check the endpoints. I got to check the boundary. By the way, for the interval, for the radius of convergence r, you take the width of the interval. So 1/2 minus a minus 1/2 divided by 2. That's your radius of convergence, 1. Wait a minute. No, that's not right. 1/2, 1/2, 1/2. All right. So we're going to check the boundary points. So we're just going to plug in x equals minus 1/2 and plus 1/2 into our series. So for x equals minus 1/2, I have the sum from n equals 1 to infinity. 2 times 1/2 minus 1/2. See, n over n. Well, 2 times minus 1/2 is minus 1. And this is my alternating p series. This has a sum that is related to the natural log of 2. This converges by AST, okay? Since 1 over n goes to 0, it is positive and decreasing. Okay, so that sum converges, so I can close it off. But notice that at 1/2, at positive 1/2, let me just get this. Okay, this diverges. This diverges by the p-test. So the sum converges for x in this interval. X is not allowed to be positive 1/2, but it's allowed to be negative 1/2. And that's my interval of convergence. Okay, so ratio test, solve an inequality, check the boundary points, and get a result. All right, a few more to go. One T is an easy one. X to the n over n factorial. Now, if you've been reviewing, you might already know that this is a series for e to the x. And we're going to show that this satisfies a nice property. So the limits here for the ratio test, set that up. All right. We cancel some stuff. So what I have left over here is just x over n plus 1. And remember, x is independent of n in the limit, so it can be shoved out with absolute value. That limit that's left over is 0. Okay. For definite integrals, when do you plug the bounds to get new bounds? So that's when you change variables. Okay, that's when you change variables. So I've done that in part 1, which will be in the VOD. Okay, just watch the VOD. You might see some integrals that I do some substitution. Same with part 2. Okay. So in general, right, when you do a substitution, you have to change the limits of integration. Okay. Let me finish this one real quick. So this one here, notice that no matter what x is, this limit is always going to be 0. So the sum converges for all x. Okay, the interval convergence is the entire real line, minus infinity to infinity, with the radius of convergence r equal to infinity. So we say that the sum converges everywhere. Okay. Now, for that new user, for that question, again, it's whenever you do a u substitution. So if, for example, I have the integral, say, from 1 to 2 of, I don't know, 2x over the square root of x squared plus 1, okay? If I set u equal to x squared plus 1, du is 2x dx. But because this is a definite integral in changing units, right? It's like going from miles to kilometers, right? 1 mile is not a kilometer, so I have to do this change of unit here. So when x is 1, okay, I plug that into my substitution here. Okay, I plug that into my substitution. And I get a new limit. So when x is 1, u is 2. And when x is 2, again, plug that back in, u is 5. And so this integral just becomes that from 2 to 5 of, what do I get here? Du over square root u. And now it's just power rule. So this is going to be 2 square root of u. If I would here, and I don't need to go back into the original units if I have a definite integral. I'm still going to get the same number. And in fact, that number I'll get here is 2 square root 5 minus 2 square root 2. Okay. So whenever you do a u substitution and you have a definite integral, that is when you have to change the limits of integration. And also, with regard to that last one that we just did, if the limit that you get out of the ratio test is 0 no matter what, then the radius of convergence is infinity. All right, let's talk some basic power series constructions here. So the basic construction, okay, we're going to start with the geometric series, 1 over 1 minus x, which has this power series representation, okay, summing from 0 to infinity. Now if I replace x with minus x to, okay, I have 1 plus x in the denominator now. And I now have this alternating series. So these are going to be our two basic constructions here. And these are centered at 0. Okay, let's note that here. Centered at 0. Okay, so now we're going to go ahead and do some basic power series constructions here. So, for example, let's look at just the very first one here, number 33 here. Let's press 1 over x as a series centered at 1. So the way we do this, we're going to actually do what I call a dirty trick. So we're going to add and subtract 1 here. We're going to add 0. So 1 over x, it's going to be the same as doing 1 over 1. So we'll have an x here. I'm going to subtract 1. I'm going to add 1. Okay, that's kind of going to be our dirty trick here. Add 1, subtract 1. In fact, if I rewrite this slightly differently, and we get something that'll work here. So that's the trick. We're going to add and subtract a magic number here. And then I'm going to factor out a minus 1 here. And so that I have this guy here. Now, the idea is that this thing here plays the role of this here. We're replacing x with 1 minus x. Okay, and actually, I'm not quite a fan of this look here. So what I'll actually do is the following. I'll go ahead and write it like this instead. 1 over 1 minus, let's see here. I mean, I guess that works. And I'm just going to use that geometric series trick here. There are multiple ways that you can do this. So here, this is going to be a sum, n equals 0 to infinity. Okay, and again here, I'm playing that role there. 1 minus x to the n. Now if I multiply by -1, I get exactly the series I need. Multiply the inside by -1. I get the series that I need. That's how you do it. Okay, it takes a bit to like understand this little dirty trick here. Okay. We'll show more of that here. In fact, I want to do 38 next, which is similar. This time it's going to be 1 over 2 minus x. And of course, for these, you can like go ahead and look at the interval of convergence and the radius convergence. All right. So let's see here. So the dirty trick here is instead of getting like a 1 plus or 1 minus, well, we're still going to force that. I'm going to factor magic 2 out. So if I factor 2 out of the denominator, what's left over? 1 over x minus 2. Okay, and now this guy in orange, whoops, does the same thing from above here. I'm replacing x with x over 2. So now I'll have 1/2 times my basic construction times my sum, okay? X over 2 to the n, and after a bit of exponent manipulation, equals 0 to infinity, x to the n over 2 to the n plus 1. Okay, so that's my series, okay, centered at 1. All right. Let's do an extension of this one here. This to demonstrate that magic number trick. So I'm going to center this at a equals 1 here. Actually, let's do -1 here. So remember that the power series to center, okay, it's going to be x minus a. So there's a minus sign built into it already. So we're going to go ahead and do, say, well, I'm basically out of room here. So at a equals 1, okay. So 1 over 2 minus x. I'm going to try to separate out a -1 out of there. So what I'll do is I'll do a add 1, subtract 1. So I think I'll add 1 here and subtract 1 there. And now take a look at what I have. 2 minus 1 is 1. I'm going to bring those outside parts in. And then I'll factor out the minus. And I get 1. Let's see, 1 minus x minus 1. So that doesn't quite give me what I want here. Okay, so now I know what I need to do. I'm instead going to combine this and this. So 1 over 3 minus x minus 1. Okay, which then I can write as 1 over 3 minus x plus 1, and then I'm going to do the 3 factor again. So 1 over 3 times 1 minus x plus 1 over 3. And now you can kind of see the construction. 1/3 times the sum x plus 1 to the n over 3 to the n, and then you can bring everything in. So it takes a bit to like really get used to like how to do these power series this way. But just remember the basic construction, and then you have everything. Now, of course, you can multiply by x and x squared. You can do term-by-term differentiation and integration, which we'll see in a second. But if you start with this basic construction, you have everything you need. Okay, speaking of which, let's go ahead and look at how to construct new power series from old. I'll only do a few of these, like probably a couple out of this section. Wait for this to load. All right, let's see here. All right, here we go. So we're looking at f of x equals 2x over 1 minus x squared squared around x equals 0. All right, so we're going to go ahead and start with a helper function, okay? Because this looks a little complicated, but let's start with a helper function here. I see a square in my denominator, and I know that when I differentiate, say, 1 over x, I get minus 1 over x squared. So that probably has come from a derivative. And we'll demonstrate that it does. Let's take a look at how that works here. Let's start with a helper function. Let g of x be the function 1 over 1 minus x. Okay? Whoops. There we go. So g of x is 1 over 1 minus x, and I know how to expand that, okay? Well, let's take a look at, like, how this develops, okay? If I go ahead and take a derivative, well, you know, take a derivative, you get 1 over 1 minus x squared. And now this almost looks like the function that we need. So if I replace x with x squared, okay, my denominator is complete, then I just get it multiplied by 2x. So now my function f of x is equal to 2x times g prime at x squared. So we're going to follow these steps here for the construction. We're going to expand g, take the derivative term by term of that expansion, replace x with x squared, and then multiply by 2x, and we're done. So let's go ahead and take a look at that, right? So I already know how to expand g, right? 1 over 1 minus x, that's our basic geometric series construction. Now, g prime. Now, we're using a theorem that says I can exchange derivative and sum and integral and sum. We're not going to worry about why. It requires a bit of real analysis. But what happens here is I'm going to take the derivative term by term in the sum. And so what that says, I can just pass the sum inside. Okay. And now I get the following representation just by the power rule, right? N times x to the n minus 1. And notice that if n was equal to 0, that term is just 0 anyway, because the coefficient. So I can start the sum at 1. Okay? So now what I'm going to do, I'm just going to follow my construction. Replace g in g prime, replace x with x squared. So now I have n times x squared to the n minus 1. Okay, and now I just, whoops. Keep replacing here. X to the 2n minus 2, just power to a power. And then the last step, multiply by 2x. So you just build new power series from old, just step by step, right? So we know that's f of x, right? 2x times this thing. All right. What happens here is I just append a 2. And then adding and multiplying by x just adds 1 to the exponent. That's my representation. That's my representation for my function f. Notice how it started from a known function and it incrementally built up to the unknown one, to the new one. Okay. I want to demonstrate an integration one here as well. We'll take arctan. Yeah, that scared me for a second. So arctan of x squared. Okay, so we got to figure out like where arctan comes from, okay? So let's think about, again, some helper functions to help us out here. Okay. Well, I know how to take the derivative of arctan. That kind of gives me a clue, okay? So if I take, so let's start with a helper function. So let g of x be just arctan of x. Then when I take the derivative, okay, g prime of x, the derivative of arctan is 1 over 1 plus x squared. That's one of my basic constructions just modified. Okay. So now let's think about what we need, right? F of x is equal to g of x squared. So if I know how to expand g, I know how to expand f. So we're going to incrementally do this. G prime is 1 over 1 plus x squared, which I know how to expand, right? Just replace in the basic construction x with a negative x squared. It's just the alternating version. So you have minus 1 to the n times x to the 2n. Now g of x, we get g by integrating. Okay. And we're going to use a theorem here again that says that I can exchange integral and sum. And so we're just exchanging the sum and the integral. That's just by, the power rule. Of minus 1 to the n times x to the 2n plus 1 over 2n plus 1 plus some constants of integration, because we need that for indefinite integrals. But because of how arctan is, we're expanding at 0. We want to make sure that the value agrees at 0. Okay, so since arctan of 0 is 0, c is equal to 0. Okay, I'll leave you for the details on that. Then, okay, what we'll do, okay, because we now know that f of x is g of x squared, so now I can just replace. Okay, being careful with these exponents here. Minus 1 to the n, x to the 4n plus 2. over 2n plus 1. That's your expansion for arctan of x squared. So again, use those helper functions, okay? Use those helper functions. Okay, start small and work big. Okay, that's all I'm going to show for like these term-by-term differentiation and integration. It's very easy to do. But now we're going to go ahead and actually talk about Taylor series, and that's going to be the end of the stream. So we're just going to do some basic Taylor expansions. Okay, some very, very basic Taylor expansions. time that this was muted. Oh boy, am I gonna have to redub? Nah, I'm probably not gonna have time for that. So, the idea again for the Taylor series, let's just run it back here, okay? For this one, let's take a look at this one here. I first find my derivatives and I find my patterns for the derivatives of the function in general. Then I try to see how I can generalize it, divide those derivatives by n factorial, and then evaluate, okay? Because remember, this center point here is the one that goes in, okay? That goes in for x. Okay, and I know that it must look like this. Now I just follow the recipe. Okay, take derivatives, right? Just like we did here. This one was easy. E to the x is easy. It has an easy expansion. Okay, sine x, you gotta alternate powers, alternate signs here. Same with cosine. Okay, be very careful with how you do that one. Okay. And of course, this 1 over x1, that's the exact same one that you get with the geometric series arguments, okay? Exact same one. Okay? I find that like the geometric series argument is like more powerful and easy to understand than the Taylor series argument here, but you get the exact same series here, okay? Just be careful about how you're going to how you're going to actually like center everything, okay? And of course with the Taylor series you can replace an appropriate number to get a brand new expansion. Say for example, if you want to expand e to the 2x, you just replace x with 2x in that expansion, just like we did with the geometric. All right. This is incredible. Almost 5.5 hours at this. I think we're going to go ahead and call it here. Thank you all for watching. Happy studying.